Hello, everyone. It's Brian. And this week I'll be presenting the paper review for our speaker, who is Ricardo Garza-Giron. And this this talk is based off of his recent paper in Science Advances. And the paper title is Solid Earth Atmosphere Interaction Forces during the January 15th, 2022 Tonga eruption. So sorry I couldn't do this live, but hopefully this recording will do. So a quick background on our speaker. He's a postdoc at the University of California, Santa Cruz, UCSC. And his research interests are primarily seismology investigations of large data sets to understand active volcanoes, large earthquakes, and structural variations in permafrost. As I said before, it's primarily using seismology, but he's also used electromagnetism and machine learning. He got his PhD in 2021 in geophysics at UCSC and his bachelor's in 2014 in geophysics engineering at UNAM. So the 2022 Tonga eruption was pretty famous. It was all over the news last year. And we all saw many images and animations like this showing just the explosion that occurred during the main eruption. And the interesting thing about this explosion was that it was so powerful. It essentially circled the Earth 3 times. So we can see here another animation. You can see the shock wave propagating outwards. And scientists essentially think this is the first time since the 1883 Krakatoa earthquake that an explosion this loud occurred during an eruption. The other dangerous thing about this eruption was the tsunami. People were worried about a tsunami hitting some of the nearby islands. And one of the interesting things about the tsunami was that they started recording the effects of tsunamis on tide gauges before they expected the tsunami to arrive. So what's showing here is a tide gauge here in California. And in green is when they expected the tsunami to arrive, but you can see the water levels start to fluctuate beforehand. And this was due to the arrival of the atmospheric wave, or essentially the shock wave that we saw in these previous animations. And so the mechanism for this is that the earthquake happens with a large explosion, and the shock wave travels faster than the actual tsunami wave. And as the shock wave passes over deeper waters, it starts to amplify. And then it creates waves on the surface of the ocean that then are slightly behind the shock wave. And essentially, if you look back here, and this is the classical tsunami, it's far behind. So this shockwave-induced tsunami, it's smaller than the classical tsunami, but it arrived at land sites and tide gauges earlier than the tsunami was expected to. And so the shockwave from this eruption was one of the more physically interesting things that happened. Other than causing a loud boom, people have studied how these shock waves and these atmospheric waves propagated. And so the main mechanism is called atmospheric gravity waves. So essentially what happens is that you get a parcel of air will rise to a certain elevation. And then as it rises, it will then sink and then oscillate back and forth as the temperature variations will cause this packet of air to move up and down. So it'll get trapped between different layers of the atmosphere. And so if you can see this in satellite images, these ripple-like effects, these are gravity waves, atmospheric gravity waves. So this is the mechanism by which these waves from the explosion traveled around the Earth. So if we think about this eruption in the historical context of the very large and most famous eruptions, we think of the 1883 Krakatoa earthquake, which I mentioned earlier. There's a 1980 Mount St. Helens earthquake, or not earthquake, volcanic eruption, and the 1991 Mount Pinatubo volcanic eruption in the Philippines. But I think the one that's most interesting for comparison is this 1883 Krakatoa eruption. So this occurred in the Krakatoa Island in Indonesia, and it was characterized by 4 large explosions during the peak of the eruption on August 27th, 1883. And the third and largest explosion was actually heard about 4,800 kilometers away, or almost 5,000 kilometers away near Mauritius. And this explosion was legendary because it has been estimated to be the loudest sound in history, and was estimated to be about 180 decibels in terms of sound intensity. And just for comparison, a rocket launch is about 140 dB. And so this is already much, much more powerful than a rocket launch sound. 130 dB is a pain threshold. So you can imagine that 180 dB, there's a lot of pain. And they've said that sailors within 50 kilometers away from this eruption had their eardrums ruptured because it was so loud. So a similar thing is happening for the Tonga eruption. And when these atmospheric waves have been studied, the waves themselves cause pressure variations all over the globe. And some groups have studied this and simulated it as shallow water ocean wave propagation. So very similar physics. And so they've realized that they could propagate or simulate the timing and the global propagation of this using a shallow water ocean wave model. However, using modeling the atmospheric wave doesn't really give you much information on what happened at the source, which is what our speaker is primarily interested in. So instead of studying atmospheric waves, what Ricardo and his group wanted to study were the propagation of elastic waves, or what seismology records, the propagation of waves through elastic media through the ground. And so we think about the mechanisms that contribute to ground motion during large earthquakes like this. There are essentially three mechanisms. So at the source where the main eruption is happening, there's a combination of implosive forces due to rapid reservoir deflation. So you can think of this as a very sharp implosion, where implosion is the opposite of explosion, a very quick collapse of the magma reservoir. So that itself will cause seismic waves to radiate. And you can also get a reaction force due to rapid ejection of material out of the main vents. So reaction force, you can imagine, is this thing is throwing out ash and lots of other material very violently from the main vents. And as you can imagine, there's always an equal and opposite reaction going the other way. So as this material is ejected, you get a vertical reaction force that then pushes on the ground. And that itself will also radiate seismic waves. So generally, both mechanisms are active during the eruption. So it's kind of difficult to figure out which the source time history of each one of these. So you can't really decouple them from recordings at seismometers. But previous studies have shown that the reaction force is actually dominant for the remote seismic waves. And other studies have shown that you can actually, by recording the seismic waves from this reaction force, you can use those to predict plume height. And this was discussed by Ricardo in his paper. And the third mechanism, this is kind of an interesting one, is that the atmospheric pressure wave, or the gravity wave, or Lamb wave, will cause vertical acceleration in seismometers. And as it propagates over land far, far away, it will also cause topography to tilt, which shows up on the horizontal motions. And so when we're talking about the ground motion interaction between the atmosphere and the ground, these first two bullet points are talking about how the wave itself will cause ground motions far away from the eruption. But what they wanted to study in this paper was how do the waves cause ground motion very close to the main volcano. And what they find, and which I'll discuss later, is that you get these resonant waves. So essentially you get periodic acoustic oscillations. So standing waves. So if you think back to standing waves, they're essentially constructive interference between waves that are sent from a source and that then get reflected back from some interface. And as they collectively interfere, you can get very large amplifications. So the standing wave here in this little animation is this black line. So at the eruption, what happens is that you get acoustic oscillations that go from the ground up to about this 120-kilometer interface, and then it bounces back and forth, back and forth, back and forth. And so then you get a very strong standing wave right near the eruption. And so what that does is then it causes a periodic source right at the volcano, which then will also radiate seismic waves. So this was first studied for the 1991 Mount Pinatubo eruption. So if we look at the data, the seismic data that was recorded, you can see very strong P wave, S wave, and Rayleigh waves, which is a type of surface waves. These are very cleanly recorded at teleseismic distances. P waves are the fastest traveling waves. And so you can study the P waves to get insight into the first 10 minutes of the eruption. And what they found was that there's very little azimuthal asymmetry. So if you look at P waves over all across the globe, you don't see many variations in terms of the waveform. So that what that means is that you get a very nice axisymmetric source, rapid vertical venting. And so that's a very strong indicator that the main seismic radiation here is due to some kind of symmetric vertical force happening at the volcano. And so to study this more closely, what they did is that they then stacked the P wave waveforms to get this representative P wave waveform here. And so you can see very strong returns at what they call event 1 and event 2. These are the first two explosions at the Tonga volcano. And so you get a nice, clean, very clean, much less noisy waveform here. And what they then did is they did a deconvolution with the elastic Green's function in order to get the source time history for vertical reaction force. So essentially, they're just estimating what the force would be through time, the force time function would be in order to generate this P waveform. And so what you see here is you get very strong force around 2 × 10 to the 13 newtons corresponding to each one of these eruptive events. And what they also found is that they could fit this equally well with either the vertical reaction force or an implosion point source. So they, like we said, there's a trade-off between the two, but here they kind of favor the vertical reaction force. So in order to study longer than 10 minutes, because if you go back to these waveforms, essentially after the P wave hits, then the main things that you start recording are the S wave and the Rayleigh wave. So if you want to study longer time motion, longer time history, you have to look at the surface waves. And so they did that. They looked at the surface waves, and then they repeated the deconvolution in order to get the source time history for the vertical reactive force. And you get basically a very similar time history as we got with the P waves, but now we get it for about 1,500 seconds. And as we see before, the first event was the strongest one, and E2, event 2, and event 3 were still pretty strong, but they're a little bit weaker than the first event. And this source time history gives pretty good predictions, very good reconstructions on the observed waveforms. So one exercise that Ricardo and his team did was they wanted to figure out whether or not these Rayleigh waves from this vertical source were truly Rayleigh waves. And they just wanted to look at the consistency between what they were modeling and what they observed. So another way to do that is to repeat the source time history estimation, but station by station. So doing an individual station deconvolution, and then getting the estimated source time function, and then comparing that between station and station. So long story short, they get very similar source history for all the stations, which basically shows that, yes, this source time function that we see here is pretty robust. And the stacking effect by combining all the stations can actually help to minimize the influence of Lamb waves, or that atmospheric wave will also show up on the seismometers, as I mentioned before, as the wave itself will go over the ground these seismometers are located, it will cause oscillations. And that's not the signal that they want. They want the signal due to the source. So by stacking these waveforms, by stacking means averaging, they can minimize the impact of these land wave arrivals. So as I mentioned before, for the first 5,000 seconds, they can clearly pick out the main three eruption or explosions. And if you bring this out further to about 16,000 seconds or 4.5 hours, you can see that they also record and estimate a secondary explosive stage, which is a little bit smaller than the main ones, but still pretty strong on its own. So then they also wanted to study the resonating acoustic modes. So as I mentioned before, this resonant acoustic modes are the oscillations of the standing waves that go between the ground and some atmosphere that bounce back and forth. So in order to measure these, look at this particular response, they know that this response is a long period seismic response. Basically, you can kind of estimate the period it would take for a standing wave to go from the ground to the atmosphere and back down to the ground. And so they filtered it to about 3 to 5 microhertz or 3 to 5 millihertz to get the long period wave motions for 0 to 20,000 seconds. And if you take a frequency analysis, the FFT, look at the frequency spectrum of these waves, of these long period responses, you can see two very strong peaks, one at about 3.7 hertz and another one, I think, at about 4.5 hertz. So this 3.7 hertz, this is the main one that's causing the standing wave, these resonant acoustic modes. So this is the one that they will try to model. And so by modeling, what they're trying to do is they're also trying to figure out the force history caused by the acoustic modes, these resonating acoustic modes. So same as they were doing with the reaction force, when they were trying to compute the force history of the reaction force, they're trying to compute the force history of the acoustic modes. So they want to see how strong can these oscillating acoustic modes be in terms of forcing the ground and causing these long period ground motions. And what they get is that it was actually pretty strong. It's about 4 times weaker than the main eruption force, but still really strong if you just think about the effect of this atmospheric perturbation that just goes back and forth. You wouldn't expect it to be as strong as the main eruption, but it just goes to show how strong these explosions were. So the physical takeaways here is that the use of the elastic waves from seismology gives the highest time resolution with regards to the source time function. So this is something that we've seen in other studies of large eruptions in the last few years or so, is that lots of people have paired geodesy with seismology in order to get really, really detailed history on what's happening in terms of the eruption, in terms of like magma motion, explosive events. So the elastic waves really gives you the best data possible in terms of teleseismic waves, in terms of resolving what happens at the source. They found about 25-second pulses throughout the eruption time history. So they don't spend too much time on the physical interpretation of how these pulses and these explosions were formed, but they do mention that it could possibly be associated with magma fragmentation due to interaction of water and melt. So anytime water and super hot melt will interact, you always get some kind of explosive release of steam, or it could potentially be dynamic changes in conduit stability. And peak force strengths from the source time histories that they estimated are about an order of magnitude larger than for the 1980 Mount St. Helens eruption. So very strong forces involved in the eruption. And finally, you can do a cross-check with atmospheric dynamics. So this was an interesting discussion that they presented at the end of the paper, was that they could say, okay, assume we don't know anything about the seismology, but we have observations of the cloud plume. And so using satellite observations of the expanding cloud plume and a 1D gravity-driven cloud spreading model, you can estimate an average mass discharge for the first 100 minutes. So this has nothing to do with seismology, but just from looking at the plume dynamics. And you can estimate a mass discharge of about 3.3 times 10 to the 9th kilograms per second, which is about the same order of magnitude as the Mount St. Helens and Pinatubo eruptions. And then if you assume a nominal discharge rate of 300 meters per second, you can compute the force due to this discharge, where the force is basically the time rate of change of mass times the velocity, and you get something that's about 10 to the 12 newtons, which, if we go back to here, was pretty much right on target. So this is basically confirming the seismological inversions are consistent with what you can get from atmospheric dynamics and plume dynamics. And this also suggests that you can do some type of even joint inversion with studies of the elastic waves and the plume dynamics on its own. So they do mention that this study probably could have been improved by having closer seismometers, near source seismometers, but at the time there weren't any at the island. So probably for future monitoring efforts, they'll be including a lot more near source seismometers anywhere there's a volcano. So that's it for the summary, and hopefully you guys can have a good discussion, and we'll see you at the speaker.